In this video, I'm going to introduce you electric charge for electric static force. So here's a video to show you the electrostatic force. It's a common force you see, especially in the winter. Um, you in the winter you have a dry air, and then you get electrostatic force. So here we have a balloon, and you see. Okay, let me borrow your head.
So we have a little kid named Kid. We love him so much. Here goes the tissue paper.
So what we see is that after rubbing the balloon on the head, the tissue paper, the pieces of tissue paper is being attracted to the balloon by electrostatic force. Um, you see that actually before even the balloon touches the tissue paper, the tissue papers actually get stuck, move, and then up to the balloon that has a friction. It has been rubbed by the hair, right? So that's electrostatic force. So this electrostatic force is known for a long time. And even in BC 600, Greeks used to call amber as electron and electron, amber. So if you rub the amber, it tends to attract some small pieces of things. So what we see is electrostatic force. Electrostatic force. I use FE, electrostatic force. It's a force, so it's a vector. It's non-contact force, field force. As you saw it, the tissue paper got attracted to the rubbed balloon without being in contact. And this electrostatic force is either it can be attractive or repulsive. So you can have electrostatic force, unlike gravitational force, which is also another field force, but a gravitational force is always attractive force. If you have two masses, it attracts towards each other. In the case of electrostatic force, the electrostatic force depends on the charges, which we're going to talk soon. It can be either attractive towards each other or repulsive, away from each other. So that's the electrostatic force. So I already mentioned that source of the electric static force. So here is the source. The source of electric force is the electric charge. We use the electric charge as Q is electric charge. And we use the new unit that's called, use the uppercase C, that's called Coulomb. One Coulomb, 2 Coulomb, that kind of a thing. And Q is the typical symbol we use as an electric charge. And it is a scalar. Different from mass, that is a source for the gravitational force. Electric charge has two polarities. It can be a positive charge or it can be negative charge. Here is the source of electric force, and that's the electric charge. Electric charge is the fundamental mental property of matter. Just like mass, right? Mass is the fundamental property of matter. Again, we've been using example between so gravitational force, right? Gravitational force acts on the mass. Force acts on mass, and electric force acts on the charge. Stick. Charge. Let me see. So here is the, every matter is made of atoms, right? And then we say inside the atom, there are smaller particles called electrons, protons, and neutrons. Inside the nucleus, you have a neutrons and protons. Outside the nucleus, you have an electron cloud. And we said that, proton and neutrons have some mass, which is larger than electrons. So those are the fundamental property of a particle. And also, proton and electron has charge. Proton has a positive charge, and electron has a negative charge. Neutron does not have any electrical charge. And this is the charge that we're talking about. It's the fundamental property of matter. So let's go back to the node. We say inside the atom, which is the fundamental, not the fundamental, but it's all the matter is made of atom. In atom, right? Remember we have a protons, neutrons, right? And electron. And symbol we use for proton is P, neutron is N, electron is E, minus. Then a charge, right? Electric charge, it's going to be E plus 0, E minus. For mass, see, these are the properties of particles. 1.7 times 10 to the minus 27 kilogram. I should write it nicer. Minus 27, 1.7 times 10 to the minus 27 kilogram. And electron is 9.1 times 10 to the minus 31 kilogram. A lot smaller. So here you see that one electron or one proton, which is the smallest of an electric charge that you can have, 1e, is 1.6 times 10 to the minus 19 that coulomb. So one electron or one proton is 1.6 times 10 to the minus 19 coulomb. Can we have, so my question, can we have, let's say 2.3 electrons? Or 126.347 electrons? No, we can't. It has to come with the 1 electrons, 2 electrons, 3 electrons, right? You can't have half of you, half of the dog. So what it means is that these charges, electric charges, are quantized. Means that you have a 1 electron. That means that you have a 1.6, it could be 1 excess electrons or 1 deficiency of electron. Then you're going to have a 1.6 times 10 to the minus 19 coulomb more, positive or negative, depends on excess or deficiency. And if you have 2 electrons lost, then you're going to have a 3.2 times 10 to the minus 19 coulomb. If you have a 3 electron lost, then you're going to have a 4.8 times 10 to the minus 19 coulomb. You cannot have the value in between. Cannot have the value in between. It's quantized. It's like a steps. There is not like a slope, the gradual change of electrons. You have to have a 1 electron, 2 electrons, 3 electrons. Also notice that electric charges are very, very, very small. Before I go into that, so answer this question. If an object, an object has a net charge of 8.0 times 10 to the minus 19 coulomb. What's the net charge? Net charge. This net charge is of what multiple? Of electrons. So if the object has the 8.0 times 10 to the minus 19 coulomb, how do you say, how many electrons is it lost? How many electrons would need to be removed to create this charge, right? The answer is that. Because you can see when you have 4 electrons, that's going to be 6.4 times 10 to the minus 19 coulomb. Then if you have 5 electrons lost, then you see it's going to be 8.0 times 10 to the minus 19 coulomb. Another thing that I want you to pay attention is that so charge is either plus or minus, and charges, the unit of a charge is called coulomb. It's the fundamental property of a particle, matter, and also it's quantized by number of electrons. Then you notice that one electron, you see, one electron is 1.6 times 10 to the minus 19 coulomb. So you, here, it's minus 19 coulomb, right? That's very, 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 very small. So you see that a charge usually really, 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 really small numbers. Imagine that though. So can you calculate for minus 1 coulomb of a charge? To have a minus 1 coulomb of a charge, how many number of extra electrons? How many number of extra electrons do you need to have for minus 1 coulomb? Calculate it. That would be about, so it's 10 to the minus 19, right? So you're going to flip it. Then it's going to be about 10 to the 18, 10 divided by 1.6. So it's going to be 6.25 times 10 to the 18 electrons you need for 1 coulomb. That's a lot of electrons. 10 to the 18 electrons. That's a lot of electrons, right? So for example, a lightning bolt is estimated to carry a charge of, what do you think? 10 coulomb. So 10 coulomb is so many electrons. So many electrons. So again, electric charge is the source for the electric force. Electric charge has two polarities. It can be plus or minus, right? Plus or minus. We use the symbol Q, and the unit for electric charge is coulomb. The unit, it's the fundamental magnitude of electric charge is come from electrons and protons, and that's 1.6 times 10 to the minus 19 coulomb. So you cannot have a 2.3 electrons, for example. So electric charges are always quantized, and also because it's 1.6 times 10 to the minus 19 coulomb for 1 electrons, electric charge is very, 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 very small. So for example, even to have a 1 coulomb of charge, that's a lot of electrons. You have to have a 6 times 10 to the 18 electrons to make up 1 coulomb of a charge. All right, so I'll see you in the next video about electric force.